is the simplest one, where we had a VCC voltage connected to the base through a resistor RB, and the same voltage is connected to the collector through resistor RC, and there is nothing else in the circuit. Yes, we do have the AC input and AC output, but those we don't care about right now. We will just remove them from the circuit when we do the analysis, and we are allowed to do that because of superposition. The superposition tells us that if there are multiple inputs to a circuit, I could keep one, deactivate all the rest, and then analyze the circuit. Then I can activate the one that I just deactivated, deactivate everything else, then analyze the circuit. So here I can deactivate the AC input and analyze the circuit. That will give me some value of IB, some base current in this circuit. That base current will determine which of those curves that we see in the characteristic output characteristic of the BJT is applicable. And then from that, I can find out IC and VCE. So this is the idea. So this was the fixed bias configuration. So any of these configurations, when I try to analyze, what I have to do is I have to separate out the circuit into the input side and the output side. How do I do that? Well, first of all, I remove the AC part and remove all the capacitors. And why are we allowed to remove the capacitors? Because in the DC domain, the capacitors act as open circuits. So capacitors can be removed. The AC inputs will be removed. All that remains is the DC part. And that from that DC part, what I did was I separated out this VCC. So it's just for analytical convenience. What I did was I looked at this circuit, removed the AC, and this VCC term, this VCC, I said that because this VCC is coming to IB through RB, and the same VCC is coming through to C, the collector terminal, through RC, what I did was I separated out VCC. So I now have two VCCs. The same thing. It's this exact same circuit as before. But the benefit of writing this circuit in this manner is that I can now clearly see the input side and the output side. What is the input side? Input side is this VCC followed by RB, then B, this B terminal. Then I have a voltage drop of VBE, which is the base to emitter voltage drop, and then finally ground. And on the output side, I have again VCC coming through RC, the resistance RC, and then I'm going down and getting a voltage drop of VCE, and then I'm finally coming downwards to the ground. And so this is the input and output loop. So always in this analysis, the first step is this, whatever I did, remove AC, remove the AC inputs, remove all the capacitors. Next, think about the input side of the circuit and the output side of the circuit. If you want, you can separate it out like this. Then the important step is to find IB. That is the most important thing. How did we find IB? For IB, I just looked at the input side of the circuit. I wrote it down. Again, I redrew it in the form of a more familiar loop. So this loop is the same as, so whatever I draw in this circuit, so this circuit is exactly the same as this input loop. So I have VCC, RB, voltage drop of VBE, and the ground. So once I have this, I can very easily find out what IB is, because IB is just the current through RB. And the current through RB from KVL, I know that IB will have to be equal to VCC minus VBE by RB. And what is VBE? VBE, from our previous discussions, we know that it's 0.7 volts. And once you find out IB, next step is to find out IC. But that is not really a step, because I already know that IB times beta is IC. So IC is what? IC is the output current. So I know the output current is just IB times beta times IB. Okay, so now what I have to do is to find VCE. Again, VCE is what? VCE is this voltage, the voltage potential difference between the C terminal and the E terminal, and that I find by drawing an output loop. So that output loop that I circled here, I just redraw it in a more familiar manner. So I redraw this thing. So there is a VCC, there is RC, there is VCE, and then there is ground. So I draw it in this more familiar manner, and I find that VCE is nothing but VCC minus RC times IC. So it's just KVL being applied, or you can think of it as VCE is this VCC, this VCC voltage is here until this point, and suddenly there is a voltage drop due to this RC. What is that voltage drop? That voltage drop is IC times RC. So you could write it down as VCE is equal to VCC minus ICRC. Actually, yeah, so here it is fine, but later on I'll make a point. Here, let's not get into that. But anyway, we now know what VCC is, what VCE is, what IB is. So once you know IB and IC, I know IB and IC. So the intersection of these 2 points. So you go to VCE and draw a straight line upwards. Go to the value of IC that you just computed, and then draw a straight line, a horizontal straight line. The point of intersection is your operating point, or the Q point. Right? So everybody clear till this point? This sort of analysis, because this is the most basic analysis, and everything else we do is just a repetition of this. Okay, so hopefully everybody has understood it. Okay, so now we did one example. So in that example is the same thing. Everything was the same except that we were given some numbers for these resistors and the VCC, and then we applied the exact same analysis to find out these values. So can somebody please confirm whether I went through this example or not? Because yesterday there was not enough time, so I skipped one example. But if there is any doubt, I can go over that. Because today is actually a tutorial, so what I intend to do is to solve some problems, but we need to make sure that everybody is clear about this concept. Because I might solve 1,000 problems, that will not help if you don't see the underlying concept, and that underlying concept is always the same. So you don't need to, just if you solve one problem, you know how to solve any other problem, because the steps are exactly the same. Okay, so I didn't get an answer, so I hope I did it. But if I didn't go through this, I have already sent this slide to you, so you could send these notes to you, so you could take a look and see whether you understand everything. If you don't, please let me know. So what we just saw was the fixed bias configuration. The problem with the fixed bias configuration is that I can take the circuit. So what would normally happen is that I would try to get a certain value of IC and VCE to determine my operating point. So if I have this fixed bias configuration, I will what I would really do is I'll try to find appropriate RB, RC, and VCC, and then try to find out what my operating point is, or try to achieve a certain operating point. Right. So generally, what we are doing right now is we are given a circuit and we are trying to analyze it. But in practice, what I would do is I would be asked to, I will be given a BJT, I will be told its beta value, and I will be told to find appropriate RB, RC, and VCC so that the transistor is in its active region of operation. Okay, so this is what I would do. So I can take the same analysis and then appropriately choose RB, RC, and VCC to make sure that all my active region requirements are satisfied. Now the problem is when temperature changes, the value of beta changes. Now when beta changes, then we know that IC will change. IC will become IB times beta, IC times IB, but then beta times IC, but then but if beta changes, then IC will also change, and that's not nice. And if IC changes, VCE will also change. So in effect, as the beta of the transistor changes, the operating point tends to move around, and this is not a good thing. I don't want my operating point to move to something very close to the cutoff region or close to the saturation region, or to make the current so high that the transistor's power ratings are exceeded. So in order to ensure that even when beta changes a bit, my operating point does not change much, I come up with all these new techniques. So the technique, so one possible technique or one possible improvement to the fixed bias configuration is this emitter bias configuration, where we just add an extra resistor to the emitter. Between the emitter and the ground, I add this extra resistor RE. And then we saw that if I take this extra resistor and do the input side analysis, finally we can show that IB, the base current, is equal to VCC minus VBE by RB plus beta plus 1 RE. Right, so now I have a IB slightly different. In the fixed bias configuration, I had VCC minus VBE by RB. Now I have VCC minus VBE by RB plus this quantity, beta plus 1 RE. So this quantity actually helps us keep the collector current same, approximately the same even when beta changes. Why? Because IC is equal to beta plus IB, right? But what is IB? Beta times IB. So what is IB? IB is this VCC minus VEE RB plus beta plus 1 RE, right? But then this term beta plus 1 is almost equal to beta. Let's write it as, so this is approximately equal to VCC minus VBE divided by beta plus 1 RE is approximately beta. So RB
Sir,
plus, yeah.
excuse me. Sir, in the left side, you wrote that VCC minus VB by
Mhm.
RB plus beta plus 1 RD. And then in
Uh-huh.
the right side, in the second step, you wrote that VCC minus VEE.
Oh, no,
I
no,
think, sir,
sorry.
it
Yeah,
will be
that's, sorry,
VE.
VBE. Yes, VBE. Yes.
Okay, sir. Thank you, sir.
Okay, thanks. Okay, so that's correct. So the VBE should be VBE. So now VCC minus VBE is, we are not touching that, but beta plus 1 is approximately equal to beta. Let's make that approximation. Okay, because beta is large. Beta can be, let's say, 300. 300 and 301 are approximately equal. Now, also the other thing is, this beta RE term is rather large. Why? Because beta is large. RE, let's say RE is also large, 1 kilo ohm also. So if beta is, let's say, 200 and RE is 1 kilo ohm, so I have 200 kilo ohms. And in comparison with that, RB is small. So what we could say is that RB plus beta RE is approximately beta RE. So I can write it as beta VCC minus VBE by beta RE. Now beta cancels. What that means is that my IC, the current IC, is no longer dependent on beta, which is a nice thing, because if IC does not depend on beta, then VCE also does not depend on beta, which is great, right? So I want to make sure that IC and VCE, the two output quantities of interest that determine the operating point, does not change with beta. So this is what is happening here. Of course, this is an approximation. So in reality, there is some dependence. There is a dependence. It's not like you cannot just say that it does not depend on beta, but approximately it does not depend on beta. So if beta changes a bit, still IC will not change a great deal. On the other hand, if you take the fixed bias configuration, then what happened in the fixed bias configuration? Fixed bias configuration, if you go back to fixed bias, In the fixed bias configuration, your IB, let's find the upper, yeah, IB is what? VCC minus VB by RB. So what is IC now? So IC is equal to beta times VCC minus VBE by RB. Now what happens if beta changes? If beta becomes double, IC also becomes double. Beta becomes triple, IC also triples. Right. So this is why this circuit is very, very sensitive to beta, changes in beta. Whereas this circuit is much less sensitive to beta. So everybody get this point? It's important to see why we are doing this, because why would I otherwise unnecessarily introduce some complexity? Because I'm taking a very simple fixed bias circuit, adding an extra resistor that, of course, I am paying more for a resistor. In terms of this analysis, I'm doing more analysis, I'm doing extra work here in the analysis. But why? Because as an effect of this resistor, I am getting better performance in the sense of this temperature stability of the transistor. I am having a transistor with good temperature stability. Okay, so this is why it becomes less. So the IC does not change much with beta. And of course, VCE is what? VCE is, I can show you what VC is VCC minus IC times RC plus RE. Now IC also does not change with beta much. So of course I have an operating point that does not move around a lot as beta changes. So this is the strength of this emitter bias configuration. This is the emitter bias. Then we discussed something called the voltage divider bias. So this is what it looked like. It looked very much like the emitter bias configuration, but there is this extra resistor in here. So if you remove this resistor R2, then what I have looks very much like a emitter bias configuration, except that now I am having this extra resistor R2 here, and instead of RB I am writing R1. So I took this circuit and did an analysis. How do I analyze this circuit? The basic principle is the same. I have to separate the circuit to the input side and the output side. So I have this. This is the input. This is the input loop. This is the input loop. I mean, it includes the RE. This is the input loop. And then the output loop. Both input and output loop contains the emitter terminal and the RE resistor. So what I would do is I would take the input side and then do an analysis. We'll try to find, I'll try to take the input side, which is drawn like this on the left, and then I will try to bring it to a form where I have a single voltage source and a single resistor, because that way I can easily find out what my current IB, the base current, is. So again, this was just done using the Thevenin equivalent. We found out the Thevenin equivalent, and it showed that the Thevenin resistance is R1 R2 by R1 plus R2, and the Thevenin voltage is R2 VCC by R1 plus R2. So now I am in a position to draw the Thevenin equivalent of the input side. Once I draw it, I found out that IB, the base current, is ETH, the Thevenin voltage, minus VBE divided by RTH plus beta plus 1 RE, a form which is very similar to the emitter bias form. In the emitter bias form, I had a very, very similar formulation. There I had VCC instead of ETH minus VBE divided by this base resistance RB instead of RTH plus beta plus 1 RE. It was there here as well. It is here, and it was there in the emitter bias as well. So we have a very, very similar form. And to find out the VCE, the method is very similar. So this is how we do it. And in this particular configuration, we did not discuss something yesterday. In this particular voltage divider configuration, you can do the analysis in a simpler manner as well, if you wish, in some cases. Okay, not always. So if you take the input side of this resistor, so if I take this of the transistor, so this was my input side. Sorry, this was my input side. So I take this input side of this, and then I draw this circle. So what I would see is that if this resistor Ri, what is Ri? Ri is beta plus 1 Re. So we defined that yesterday. Well, so if you have a resistor Re like this, on the input side, it appears as beta plus 1 Re, beta plus 1 times Re. That is because when you are writing the KVL, you are writing Re times IE, but IE is beta plus 1 times IB. So when you calculate, write everything in terms of IB. This resistor, instead of being Re, it becomes beta plus 1 Re. Okay, so this is what happens in this particular configuration, the beta plus 1 Re. Okay, so now if you have this Ri much larger than R2, R2 is that resistor that we put there by design. Re is also by design, but beta is a parameter of the transistor. So now if this resistor is very large as compared to this R2 resistor, then what do you think will happen to the current? What can we say about I1, I2, and IB? We can say that I1 would be very close to I2. Why? Because we have this current I1 coming in this way, so I1 is flowing here. Then when it reaches this point, it has two ways to go. Either it can go this way or it can go this way. In this direction, it is having a very high resistance. So current always tends to follow the lower resistance part. So higher the resistance, the less current will flow through that branch. So if this branch has a very high resistance, then IB would be very small as compared to I2. I mean, that is true even in a normal circumstance, IB is a small value, but here, if Ri is so large that IB is extremely small as compared to I2, then what we can say is that this loop, this circuit on top looks like this circuit here. You have this VCC and there is nothing flowing here. So it acts like an open circuit. Basically, you have an open circuit across the base terminal, base and the ground. Okay, so what is furthermore? What is this voltage? This voltage right here is the base voltage, right? Because this point R1 and R2, this joining point of R1 and R2, this meeting point is what? That point is connected directly to the base. This meeting point of R1 and R2 is connected to the base. So whatever voltage develops between this point and the ground, that is the base voltage. Right? So this is what we are saying here. Let it be written here for the future. Okay, so the base voltage is just this, and we are making the assumption that IB is equal to 0, is approximately 0. Definitely not 0 actually, but it's approximately equal to 0. So what is VB? This VB is approximately R2 VCC by R1 plus R2. So everybody sees that, I hope, because what is VB? VB is the potential drop across R2. But what is the potential drop across R2? Potential drop across R2 is R2 times this current I. But what is I? I is VCC by R1 plus R2. Right? So you have VCC divided by R1 plus R2 is equal to R2. Fine. So you have this setup where VB can be expressed in this manner. But now just we have to keep in mind that if you want to make this approximation, we have to first check whether this resistor is indeed much larger than R2. So normally the rule of thumb is that you check whether beta times Re is much larger than R2. Okay, so this is the standard. So in reality, what we want to see is whether Ri as I said, whether this Ri is much greater than R2. What we will check is whether Ri is 10 times larger than R2, right? Mm, but beta, what is Ri? Ri is beta plus 1 Re. But beta is very large, so we can approximate it as beta Re. So, where is it? Yeah. So we can write down that beta times Re should be much greater than R2. Yeah, in general, we would say that it should be greater than 10 times R2. So beta plus 1 Re is greater than 10 plus R2. If this is satisfied, then we can go ahead and use this approximation. Vb is just R2 times Vcc by R1 plus R2. So by now you might be seeing that there's a lot of approximation involved in this course. So in electronics, it's all about approximations, making the right approximation. So if we just go ahead and make some weird approximation, that will probably give us the wrong result. But if we are making the correct approximation, then analysis becomes much easier. So it is very different from, let's suppose, the probability class that you just had. So in mathematics, you don't make approximations unless absolutely necessary. There it's all about precision. And here in engineering, it's somewhere the other way around. We are making approximations whenever possible. We are always looking out for what simplifying approximation we can make and not lose accuracy so badly that our design doesn't work. So that is the base important art that designers learn. Okay. So anyway, we know VB now. So once you know VB, finding out the other parameters is very easy. So what is VE? VE is just VB minus VBE. Does it make sense why VE is VB minus VBE? Because this point is VB, this point is at VB. Then from this point to this point, there is a VBE drop. Then you get this point E. So going from point B to point E, I started out with a potential of VB, then I had a potential drop of VBE, which means the potential at E is VB minus the potential drop of VBE. So if you're not clear about this, just ask me, but I hope it will be okay. Then what is IE? Emitter current. Emitter current, again going back to the circuit, IE would be the potential at point E, which is VE, divided by this resistance RE. Actually what it is the potential at E minus the potential at this ground divided by RE, but ground potential is 0, so I can say that this current IE flowing through this is IE flowing through the emitter is VE by RE. Okay, so this is how you find things. Then ICE would be approximately equal to IE, and VCE is VCC minus IC, RC, RE. So I think you will be, we have already discussed this, why this is the case. If you don't understand something, again, feel free to ask me. So given a circuit, we might be asked to find the operating point. So take this circuit, for example, and how do I find the operating point for this circuit? So let's suppose we are given this circuit, and the question is find the operating point. How would you find this? Can somebody tell me if this is a question I give you at this point to solve? How would you solve this? Can somebody tell me what would be the first step?
Remove the AC connection.
Yes, you remove the AC connection, AC voltages, and then you also remove the capacitors, right? What you would be left is this part. So this inner part is what it will be left with. This part, so you just this part. This part you will be left with. Okay, so next, what are we going to do here?
Separate the output and input.
Yes, so you think of it in terms of output and input. But so once you do that, so for this particular circuit, actually, this is exactly the same as the voltage divider circuit, right? So in the voltage divider circuit, you divide this into input and output. What you would get is a circuit. So the input side would be, so the input side would be just this part. So this is your input side. So when you're comfortable, you can just think of it this way. So the input part is this. So everybody agrees that this is the input and nothing else is there in the input. Okay, so now this input part, if I write down, how would it look like? It will look like something like this, right? 22 volts DC, 22 volts goes to this 39 kilo ohm. And then I have a 3.9 kilo ohm to the ground. And then finally, I have this VBE terminal. And then finally, I have this 1.5 kilo ohm resistor. So this is the input circuit. So this is the input side. So now I want to find out what potential this is. This potential VB or potential VBE. However, or the potential, yeah, the potential. Basically, I want to find out. Final goal is to find out the current.
Sir, could you please repeat that how you made the simplified circuit?
Okay. So let's go back to our original discussion then. So what this circuit looks like, this circuit is just the, so whatever circuit I drew over here is this circuit, right? It was a voltage divider circuit. You had a VCC, then there were two resistors, right? So that's circuit. Let's draw it somewhere here. So this circuit, the input side is whatever I circled, right? So that part I hope is clear. So now how exactly is this circuit? What is going on in this circuit? First thing is there is a 22 volts source. There is a 22 volt source, right? So that, right, it is a 22 volt source. Next, that 22 volt source, so there is a 22 volt source carrying a current IB. So there will be a current IB. Sorry, not IB. Sorry about that. So 22 volt source, it is connected to a 39 kilo ohm resistor, right? So this 39 kilo ohm, this R1. I have 39 kilo ohm resistor. That 39 kilo ohm resistor's other end is connected to the ground by through this 3.9 kilo ohm resistors. So this point, is this clear till this point? So I am just drawing this 22 volts. So this 22 volts is nothing but there is a voltage source, right? So this is just something like this. 22 volts is the equivalent thing. So this 22 volts I am writing as a voltage source, a proper voltage source that has a ground connection, because that is what is meant by the 22 volts VCC, right? So till this point, now what happens at the meeting point? This meeting point is there, right? So this meeting point, where does it go? This meeting point goes to the base terminal. So this is the base terminal of the resistor, right? Now from there, from base, I go all the way to the emitter terminal. So going from base to emitter, so I have this emitter terminal. So there is actually a voltage drop of VBE. Let us see how I drew it in the other picture, but yes, it is the same thing. So you basically have a potential drop of VBE. This is the VBE, which is equal to 0.7 volts, right? Now, from there, you have a resistor 1.5 kilo ohm, right? So is this clear? This sort of diagram? How I
Yes.
Yes,
got from this point? Yeah. Okay. So this is what it is going on. Now, what is the base voltage, base current? Base current is this IB. Fine. So now I have a very easy to solve circuit. I'll just connect it this way, so it looks like exactly the kind of circuits I'm more familiar with. So this is the circuit. It's a standard circuit. So my question is, given this circuit, what is IB? So that's my question. So that is super simple to find out actually. And how do we do it? I mean, you could actually do whatever you want. You could solve it anyway. But in our theoretical discussion, we discussed that we would do it using the Thevenin equivalent. Because I want IB, so I would just determine the Thevenin equivalent of this part. So that Thevenin equivalent, if I draw, it will look like this. So I'll have a Thevenin voltage, I have a Thevenin current, a Thevenin resistance, and then there will be a base current flowing into the base. So it's exactly what we have just seen. So this circuit right here is this. I will just draw a Thevenin equivalent. And what is the Thevenin equivalent? The Thevenin equivalent, you could go through the steps. We saw it in the theory discussion as well. You could go through the steps, but this Thevenin voltage is just the open circuit voltage across this point. What is that open circuit voltage? It's this VCC 22 volts times this 3.9 kilo ohms divided by 39 plus 3.9. So I would urge you to confirm that this is correct. So once you're convinced, then it'll be very easy to do it next time. Okay, so you have this VCC, Thevenin voltage is this R2 VCC by R1 plus R2, and it turns out to be 2 volts. And what is R Thevenin? Thevenin resistance is the resistance that you see when you look into this side. So from the right, you are looking into these two terminals, this base and the ground terminal. Remove the voltage source by making it a short circuit, and then look leftwards. Whatever resistance you see is the Thevenin resistance. And what is the Thevenin resistance? That is the parallel combination of 3.9 and 39 kilo ohms. And that is your 3.55 kilo ohms. So once you have that, you come up with this circuit. You know E Thevenin, you know R Thevenin, you know VBE. What is VBE? VBE is 0.7 volts. So I know all these terms. So finding out IB is a piece of cake. It's this E Thevenin, this voltage minus this voltage drop divided by this resistance, right? Sorry, this resistance plus this RE resistance, beta plus 1 RE, because beta is this thing. So what you could do is, at this point, after you get this point, if you want to be absolutely certain,
sir, you are muted.
Sir, you are muted.
okay, okay, thanks for telling me. So fine. So basically, once we have this Thevenin equivalent, what we could write down, the way we could write this thing down is, we could write a KVL equation for this. What would the KVL look like? Well, for finding out the KVL, I need to know what the voltage drop across these resistors are. What is the voltage drop across R Thevenin? That's R Thevenin times IB. What is the voltage drop across RE? Voltage drop across RE is RE times the current flowing through RE. Now here, that is the tricky part, because we often tend to think from our typical analysis that if current IB is flowing here, then the same IB would be flowing here. We tend to draw these loops, right? But now what is actually happening is that we are just looking at a part of the circuit. So you have IB flowing through R Thevenin, But on the other hand, there is some IC also coming into this VBE point, right? So basically what emitter current you get is this base current plus the collector current. So as a result, your IE is equal to, RE is carrying a current IE, not IB, and in IE can be expressed as beta plus 1 IB. Okay, so this part is very, very, very important, because if I forget this, then my analysis would be wrong. So anyway, when I have this, I can write down the KVL equation for this. So a KVL equation would say that E Thevenin minus IB, IB R Thevenin minus VBE minus minus beta plus 1 IB into RE. So I'll solve this equation for IB. So this is the KVL equation, right? So KVL equation, if I solve, then I will get this IB. So this is the IB, and then I substitute all the necessary parameters, because I know every parameter here. So I will just solve, give all the parameters, and then I will solve for IB. So once I know IB, I know IC. IC is just beta times IB. Once I know IC, I know VCE. VCE is VCC minus IC times RC plus RE. This was done in theory, but you could also look at the output side of the loop, output loop, this side, and the output side you write down the KVL equation, make the assumption that IC and IE are approximately the same, and then you end up with this VCE. All right, so this is how you solve these solve these problems. So you could do it for any problem, anything you want to, any circuit you want to solve, you could use the exact same procedure. All right, so now let us try to solve one